When watching some videos of images of the universe, the viewer can get the mistaken impression that the universe we are talking about would be illusory. The universe is real, and it's still there. The problem would have been established when our brain was prepared to interact with reality. For some inexplicable reason, this interaction does not occur in real time. In other words, interaction takes time. Our memory would have been structured around that time. To be visible, the particles must first be illuminated. Every illuminated particle would, then, have a dark companion. Only after its illumination would the particles enter into relative motion, abandoning their previous condition of being stationary at their origin. Along with enlightenment, the concept of time would have arisen. Thus, for relative motion to exist, it is necessary to determine the position of the illuminated particle in more than one time, or in successive and independent moments. That would be the current definition of instantaneous velocity. Time is normally considered, by the theory of relativity, to be the fourth dimension. However, without time there would be no third dimension, represented by depth, nor any other dimensions, besides breadth and length. This becomes perfectly noticeable in the physics description for the future outcome concept of a massive event. The circular waves of light, which departed from the source, would overlap over time, adding depth to space, represented in the figure of the straight cone. The depth of the cone comes after we add time, not before. As the flow of time from the future to the past, passing over the present, is an illusion that would be sustained by our memory, the third dimension would also be illusory. You see, the future doesn't exist for us, because it hasn't happened yet. For its part, the past no longer exists. Let's take a ride on the illusion of time to show that events, observable on an astronomical scale, would have a direct connection with the subatomic level of matter. When the arrow at time points to the past, or to an event horizon, time should dilate, following the redshift of light. In the opposite direction of the arrow, or into the future, time should contract. The unification of these two levels lies in the fact that the light of a distant star must already be available to us, so that it can be perceived by our telescopes. The same condition of local light scattering is necessary for us to observe a subatomic particle, such as an electron. Thus, it would not matter the time that the light of the star could have needed to reach its summit, nor the tiny lapse of time that the light, scattered by the electron, spent to impress the eyes of the operator of the quantum system. This unifies the structures at the level of observation, and, in both cases, it is not possible to guarantee that the light would have moved absolutely in space. As you can see, time and light seem to be intertwined. So much so that the time that separates us from a distant star is measured based on the limited speed of light. In this case, the illusion of time could be related to the packing of light, also known as quantization. This process would be absolutely essential so that our measuring devices could register the presence of light. The notable coincidence is that it has already been demonstrated experimentally that the quantization of light, or cosmic radiation, does not require measurable time. That is, if light packing required time, it could not be measured. Thus, there would be an imperceptible disruption of the space-time continuum at the subatomic level. As we've seen in previous videos, this could also be extended to the macrostructure of the universe when it comes to observation. It's just that, in both cases, we depend on remote light tracking. As the real direction of the arrow of time is always in the direction of the future, this arrow should always be pointing to the subatomic level of the matter, because the information about our past is projected in the celestial vault. That is, in the opposite direction. As time contracts at the subatomic level, the difficulty of illuminating a particle will increase. Since, for that, we need shorter and shorter wavelengths. Without illumination, the particle would cease to exist for us, even though it is there. So, there is a technical limit to its observation, and, beyond that, many particles would remain obscure. This limit, imposed only on the observer and not on the universe, does not imply that time has reached absolute zero. The tendency of time to contract would be suspended at infinity, preserving the curvature of space and the principle of uncertainty. The impossibility of time contracting to absolute zero would also preserve the apparently continuous functioning of our memory, which depends on the direct measurement of time. On the other hand, if the tendency of contraction of time were suspended to infinity, it would force us to be virtually exiled in relation to the real plane of the dark matter universe, placed beyond the limits of time. Thus, when one defends the idea that the universe was static in its origin, it does not necessarily mean that time had reached its zero point. As we are talking about illuminated particles, either in the macro or in the macrostructure, we must remember that, if the universe were expanding and the light was tending towards the infrared, this could not be happening in real time. It's just that the arrow of time would already be pointing towards the past of the vault of heaven. The illusion associated with light is that during the expansion, space would be increasing its curvature in real time. It would be more correct to think that the galaxies seem to be moving away from each other because space would be losing curvature accompanied by the contraction of time. If the motion of galaxies resulted from the increasing curvature of space, it must necessarily be stretching. As this movement is confused with that of the redshift of the radiation, there could be no acceleration of the movement of the galaxies, since the stretching would be accompanied by an increase in the elastic potential energy. This does not occur within space-time. This energy arises when you stretch a spring. Everything indicates that the acceleration would be compatible only with the loss of curvature of space and with a constant drop in potential energy. Particles would accelerate because space would be relaxing after being stretched. Thus, it seems that we would indeed be seeing the universe expand, but this would happen outside the actual time of the event. That is, it cannot be said that inflation would be occurring here and now. The acceleration that seems to accompany the separation between the galaxies would be due to the fall in potential energy, which would be expected only during the contraction of the spring of space.